Mhm. Hello, everybody. This is Professor Lei, and this is the summary to the sections on a couple of applications of tangent lines. And in particular, we're going to look at using tangent line to make approximations. And another one is we're going to look at using tangent line to for the Newton methods for finding roots. Okay. Um, so we start examples and we'll have derivative of this x squares 2x, and we can find the slope at the point 3, x equal to 3. Then we can find the equation of the tangent lines easily. Okay, and in we remember we use these notations for evaluations when we needed derivatives and evaluated at x equal to 3. So a reminder of that notation we're going to use. Now, if I plug in the slope at the point which is a x equal to a, which is f prime of a, and this is the slope of the tangent line, then I can write the equation of the tangent line explicitly. And if I put this in a close-up of what's happening at a point A, and I have the tangent line, which is the red line. And we're going to use that to estimate points, say some number B that's very close to A. We're going to estimate what FB of. On the picture, we try to estimate how high up to FB is. And sometimes it's difficult to calculate directly, estimate for that. But then what we can do is use the replacement of the points on the tangent line as an estimation of what f of b is. And I shall call that point t of b. Okay. And of course, the closer the point B is to A, and the difference between the estimation, the error, is become smaller and smaller. Okay. And secondly, and because the tangent line is linear equation, so it's very easy for me to find out what plugging the number b into a linear equations are easy things to calculate, as opposed to plugging the original function f, which might be very messy. And so how do we find that the point and t of b? Well, got a couple of ways of doing this. One way is that I actually go find what the equation of this line is, which is this equation, and plug in b over here. And that actually involves a little bit of work, but there's a shorter way of doing it, and we're going to do it that way. So for examples, and here's how that approach is, you find the tangent line at x equal to 0 for sine of x, which is just y equal to x. So for x very small, the value for sine of x is roughly x. That's in fact what we have for term of limit, remember? And now another method is that we find this first. That is, as the point change from A to B, go from A to B, what's the corresponding change on the tangent line? Well, that is easy to calculate because I know what the slope of this line is. And that amount, if this is delta x, and that amount delta t is just going to be the slope times delta x. But the slope, of course, is just f prime at point A, so times delta x. Okay. That can be calculated easily. Okay, and we're going to set our notation up in the following manners. And remember that we have the derivative notation dy dx. And now we're going to set geometric interpretation, the dx, to be the same as delta x. Okay, that is the change in the independent variable x. And we're going to set dy to be this change on the tangent line. Notice this is different from the actual delta y. dy is estimations via the tangent line, how much the error is. Okay, not how much the increment is supposed to be. Okay, and of course, the dy simply in terms of notation, dy is roughly the length, not the length, the slope, L, which is the derivative times the dx, the delta x. And in general, we write it in terms of this, and we say in general the dy, the difference on the tangent line from A to B, is roughly equal to the slope times the change in the x, dx. And this relation, we call this the differential relation. And remember that the dx, dy basically is delta x, delta y, but with the quote unquote for very small delta x. Okay, so that's a difference between dx and delta x. Is dx means very small. Therefore, we cannot even call them difference dx. We call them differentials. And these four relations, we call this a differential relation. It's a very small x change versus a very small output change y. Okay, and this is we'll go. Part of differential equation, it talks about differentials, relationship among these small amount of changes. Okay, so here's an example. Here's a function, square root of x, and here's its derivatives. And so the relationship between the small change dy and dx is multiply the dx to the other side. Now, remember, dx is the same as delta x, so I can multiply this across the other side. I thought it's a legitimate fraction. These are actually geometric measurements on the graph. Okay, and in particular, of course, these change relationships at each different number for x, the numbers. The coefficient works out, the slope works out different. So when x is equal to 4, then the differential dy is 1/4 dx. And this basically say at x equal to 4, if I change x by a little bit, the y change to approximately 1/4 of that little change, amount of change. Okay, at x equal to 4. And at x equal to at x equal to 9, so let me just continue. Suppose I say at the point x equal to 9, then dy is going to be 1/6 dx. Okay, 9 to the minus 1/2 is 1/3 times 1/2 is 1/6 dx. This means at x equal to 9, if I change 9 a little bit, fluctuate and to look at neighborhood around this, I change this dx a little bit, the corresponding change in the output is 1/6 of the exchange. Okay, now we can use this to approximate. How? Suppose we know how to calculate square root of 4. It's very easy. But what is square root? It's 4.01. Let's put them a little off. What does the 0.1 change in x will cause in the change in this square root away from 2? Well, here we go. And we use the differential relations, set everything up. Delta x is the same as dx. And we have dy is 1/4 dx over here at x equal to 4. So if the dx is 1%, 0.01 times 1/4, so it's 1/4 of 1%. That's the dy, and that's approximately the change in the delta y, the increment, the real difference. So the approximation for the answer there for the square root of 4.01 is the original 2. original square of 4 is 2, and 2 plus the amount of change. This is 0.0025, so we get 2.0025. So it's approximations. And if you use your calculator, you find out, oh, that actually is a pretty good approximation. Okay, so this is how we use a tangent line to approximate values of various functions at points. Usually, the homework is related to where the points, it's some points that its neighbor is very easy to calculate. For instance, square of 8.95 is neighbor square of 9. Yeah, I know what that is. But what happens if you're off a little bit? 8.995. What's the adjustment you have to make? The dy. What is the dy? You need to adjust the 3 with. Okay. Now, here's another examples of the application using tangent line. It's Newton's methods, approximating roots, finding roots. And we start with the pictures. Okay. Suppose I want to find the roots. I know somewhere between in this blue area and the curve, there's a root. It crosses the x-axis. So x at r, and the function is 0. Okay, I want to find out where it is. So on the picture, we're going to do the following things. We're going to select some points that say close to the region where the root is supposed to be, and we calculate its tangent line. Then we calculate the intersection with the x-intercept of the tangent is. We locate these points. We call this point x2. We'll keep doing that, and go up to the points on the curve and draw the tangent line at that point and find where the x-intersection is, and then that's the third point. Then again, I go up and find the tangent line. And then if you look at the pictures and geometry, you have this series of tangent line, and that funnels the points into these corners, which zooms on the root at x equal to r. Okay. When we carry this out, this process of, we can actually calculate a formulas that is what is each individual point is depending on the previous points, and that's formula is this. The m plus first, the next point actually is the same. It's going to be, it's the present point minus these adjustments. Minus or plus, depends on that number comes a plus, positive, negative. Okay, so let's, for instance, here's a graph of x cubed minus 3x squared minus 5, and somewhere between 2 and 4, there's a root. We try to estimate where this point is going to be right there. Okay, so we start out with 4. We're plugging 4 into the first number. We're going to use this as first number. So plugging 4 over here and minus f4 and f prime of 4. We'll calculate that. Okay, and that will give me the second point, the intersections with x. And keep doing that for the third points. Then this is what we come out with. If we do it only 3 times, okay, you get roughly 3.432. If I use a software, use a tracer, actually come out to be 4. Roughly these. So from this work, we see that in this case, that after 3 approximation, it's pretty good. We already got the first 2, first 3 almost correctly after iterating 3 times. Okay. Does this work all the time? No, it might not work. And and so sometime you might get a situation where the points over x1, x2, x3 it goes further and further. Suppose, for instance, if I have a curve look like that, I start over here and I find the tangent line, and it comes in here, and it is here's x1, okay. and here's x2, but the curve x2, but the curves like these. No, sorry, not that way. On the other side, but the curve comes out like these, and so when I do it again, the tangent line keeps going, hitting the points on the other side. So I can make my curve this way, so the tangent line keep hitting the curve with points marching away from the roots, original roots we're trying to get. So there's all kind of possibilities. So in Newton's methods. But we're not going to talk too much about it. And that's it. Okay. Bye-bye. And do the homework. Bye.